Okay, in this video we're going to be looking at vectors in equilibrium. So let's have a look at this question first. We have been told that three forces are applied to a body. One has a magnitude of 300 newtons and acts due south. And I'm going to take this question step by step. I'm going to read a sentence and then draw a relevant diagram for it. So let us first talk about this 300 newton vector that is acting due south. Okay, and it's applied to a body. So let's suppose we have a body like this. Okay, we have some object B, all right, and we're applying some force to it. If we're applying a force 300 newtons due south, that means you have some sort of pulling action downwards with a force of 300 newtons. Okay, that's all that first section is talking about. Let's keep reading. Another has a magnitude of 250 newtons and acts on a bearing of 50 degrees. So it's still acting on this body here, okay, but this time both the magnitude and the direction are different. Let's start with the direction, because obviously we can just adjust the size of our vector to talk about the magnitude, but what about the actual direction? Well, relative to this body, if we drew a dashed line upwards to signify that this is north, the angle clockwise from north is what the bearing is. So 50 degrees true from the north would mean you draw a line north and go 50 degrees clockwise. And 50 degrees clockwise is roughly over here, not to scale, but it would look something like this. Okay, so that would be at an angle of 250 newtons. Sorry, it would be at an angle of 50 degrees. Okay, and the newtons would be 250 newtons. Okay, if all three forces are in equilibrium, determine both the magnitude and direction of the third force. And the third force, I'm going to do it in green. Okay, so what does equilibrium mean in this context? Well, if we have a look at the question, we're told that two forces are applied on a body, and that body is right over here in the center. If all three of the forces, right, the third force could be here, 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 God knows where, but wherever the third force is, okay, we're told if it's in equilibrium, then all three of the vectors will simply cancel out, and the body will just remain stationary. Because so far, we can recognize if we're pulling in this direction and in this direction, the body will somehow move in between them. It'll move in between these two directions at a different direction and magnitude, obviously. So we want to find the vector that cancels out the resultant. We want it to be such that the body doesn't move at all. In other words, we want to find what vector such that vector 1 plus vector 2 plus vector 3, okay, will simply yield us with an equation that says 0, 0. So this is what it means for all three of the vectors to be in equilibrium like such. So let us now work out how to determine these vectors in component form. Okay, that way our lives will be much easier. Well, let's start off with the blue vector. We know the blue vector is simply having a downwards vertical component, and it is not moving left or right. There is 0 horizontal components. So the vector component form of this, which I'll just say is vector R1, or in this case, I'll say, what did I say before? I'll say it's vector V2. Okay, V2 is simply going to equal to 0 minus 300. The reason for that is because, again, there's 0 horizontal component, and we're only acting downwards 300 newtons. So that's what vector 2 will be. Now, vector 3, sorry, in this case, what was orange? Vector 1. Okay, vector 1, okay, we need to work out both the horizontal component as well as the vertical component. Now, a shortcut you can use is anytime you're told what the bearing and magnitude of a vector is, always draw a right angle triangle. Okay, so I've drawn a right angle triangle like this. And if you know that this angle here is 50 degrees, then you know this angle here is 40 degrees. Okay, so let me just clean it up. If this angle here is 40 degrees, you can simply say the base of the triangle is 250 cosine of 40 degrees. And the height is simply 250 sine of 40 degrees. Okay, and that's just using the unit circle and some basic trigonometry. You can derive this. But that's how we can easily get what the vector is going to be. So in this case, it's simply just going to be 250 cosine 40 degrees, 250 sine of 40 degrees. So that's what vector 1 is. That's what vector 2 is. Now we need what vector 3 is. How do we work out what vector 3 is? Well, we don't. Okay, that's the whole purpose of this question. We don't actually need to know what vector 3 is straight away. We know that the sum of these three vectors is going to equal to 0, 0. So can't we just rearrange this equation to solve for v3? Well, yes, we can. So if we wanted to do that, if we wanted to solve this equation for v3, what we would get is v3 is simply equal to 0, 0, and then minus vector 1, and then minus vector 2. Okay, and I should have put a little squiggle under these as well to show the vectors. So now I can solve for what the vector v3 is, which is what the question is actually asking me to do. So let's now do this. Okay, we knew, let's just have it up like this. We knew, I'll do it all in a different color, in light blue, maybe purple. Vector 3 is simply going to equal to 0, 0 minus 250 cosine of 40 degrees, 250 sine of 40 degrees, minus 0 minus 300. Okay, and now all we have to do is minus the I components together, minus the j components together. Okay, and if we put this into our calculators, what we should have, we should get the vector minus 191.51 and 139.30. Okay, so this is the vector and component form that we get for vector 3, and I'll actually change this color because it's a little bit annoying. Okay, so this is the vector we get as vector 3. So now that we have what vector 3 is, we're still not done. Okay, what we have to work out is determine both the magnitude of the vector as well as the direction. Let's start with magnitude. Magnitude will be a bit easy. So in this case, we want to work out the magnitude of vector 3. All we have to do is do the square root of the I component squared, so minus 191.51 squared, plus 139.30 squared. Okay, and this is just simply Pythagoras. If we draw a right angle triangle, that's how we can derive it. And the answer to this is 236.82 newtons. So that's how we work out the magnitude of this vector. Now we need to work out the direction. Direction is a little bit trickier, but it's still pretty straightforward. If I were to plot vector 3 on a Cartesian plane, okay, so if I were to plot it on a Cartesian plane, which quadrant would you expect the vector to be in? Well, let's have a look. The I component is negative, so we're in the negative direction for the I component, and the j component is positive, so we're going positively upwards. So we know we're going to be in the second quadrant. So now what we can do is we can recognize we have some sort of a right angle triangle, where this is our actual vector, okay, and the horizontal and vertical components are drawn as following. If we can work out what this angle here is, the inside angle of this triangle, our life will be very simple to work out the bearing. Okay, so let me just draw a permanent diagram. Okay, so this is I component, j component, and I component. To work out this angle here, we can simply do the j component divided by the I component. And I'm just going to take the positive I component because in this case we don't really care about the negative. We just want the reference angle. So now what I'm going to do is what is the tan inverse of the j component, which is 139.30, divided by 191.51. We get 36.03 degrees. So that's what this inside angle here is. Okay, that's what we have over here. But we care about the bearing. Okay, the question clearly asks us, determine the magnitude, which we worked out, and the direction. And they gave us the directions in bearings, so we might as well give it in bearings. To give the final angle in bearings, we draw a line straight up north, and we go all the way around in a clockwise direction to work out what this angle here is. Well, we know that this angle here is simply 270 degrees, and we can simply just add x onto it. We can add the angle we just worked out. So the final direction, okay, the direction is simply just going to be 270 degrees plus 36.03 degrees. And that'll give us 306.03 degrees. So this is the direction of our third vector, and this is the magnitude of our third vector. So that's how you do this problem over here. Okay, this is our next question. So we've been told we have three vectors, A, B, and C, drawn in the figure above. And our goal is to work out what is the magnitude and the direction of the resulting vector that stems from each of these. So this isn't a question in equilibrium, but it is a question on resultants. So the first thing we need to do is let us just work out each of these vectors in component form. Now again, if I have a vector, right, with a certain magnitude, and I know the angle it's working in from the positive x-axis, okay, the formula I can work out, so let me just draw a different diagram. If I have a vector like this, okay, where it has r, magnitude of r, and the angle from the positive x-axis like this is theta, then this vector here, okay, the vector for r, can be written as the magnitude of r cos of theta, magnitude of r sine of theta. Okay, so that's how I can represent this vector in component form like this. So let's just do the same thing up here. So first thing we're going to do is we're going to work out, okay, I'm going to use a different color separately, red. We're going to work out this angle here, okay, because it's the angle from the positive x-axis. And that angle is going to be 130 degrees. So to work out the component form for the vector in green, I can simply say, okay, the vector component form is going to be 12 cos 130 degrees, 12 sine 130 degrees. And this vector here is the component form for vector A. Then we can do the same thing for vector C. Okay, for vector C, we can clearly see, no pun intended, that the angle is 15 degrees from the positive x-axis. However, we're going in a clockwise direction, so technically it's actually negative 15 degrees, okay, because 15 degrees would be up here, okay, but the actual direction relative to the x-axis is negative, because we're going in clockwise direction. So we can say this vector is simply 17 cos of negative 15 degrees, 17 sine negative 15 degrees. Okay, so that's the component form for vector C, and now let's do vector B. Okay, to work out the component form of vector B, all we need to work out is one of the following. Either what is this angle here, or what is this angle here. And because this one's shorter, I'm just going to work out this one here, because I'm too lazy. So to work out what is this angle all the way around here like this, we can simply say it's the same as 180 minus 55 degrees. And 180 minus 55, that would simply give you 125 degrees. So this angle here is 125 degrees. So the component form for vector in purple, vector B, is simply going to be 10 cos of 125 degrees, 10 sine of 125 degrees. Okay, so now we have all three of these in component form. And our goal is to work out the resultant vector. So let's also just first do that. To work out the resultant vector, in this case, what we can simply do is add all three of these vectors individually. So we can add this vector A here with vector of B plus vector C. And this will give us our resultant vector. And once we do this, what we get is, actually I have made a mistake, it should be negative 125 like I said here. Okay, so it should be negative here and here, and it also should be negative here and here. Okay, so now the final answer that we get is 2.97 and minus 3.40. So this is our vector in component form for the resultant. So now we just need to work out what is the individual magnitude and direction of this vector here. So the magnitude is pretty straightforward. To work out the magnitude, okay, to work out the magnitude of this final vector, we can simply just say it's the square root, again, of the I component squared plus the j component squared. And that would give us 4.51, we'll say 5 newtons, or just anything in this case. And the direction, okay, to work out theta, we're simply just going to do the j component divided by the I component, but the tan inverse of that. So what we get is 48.84 degrees. Okay, and that's not the actual angle. 48.8 degrees is the angle that we get from here. Okay, so we get that it's the angle from the positive x-axis like that. But what we actually want, okay, is the one in this quadrant here. So to work it out, we simply need to work out that positive I component means we're going positively in the I direction, and a negative j component means we're going negative like this. So we're technically in the third quadrant. And we know if I have an axis like this, the reference angle is simply 48.84 degrees. Okay, so if we want to give the angle as a bearing, we can say to work out this angle as a bearing, we just do 90 degrees plus our value for theta. Okay, so the direction here as a true bearing is simply 90 degrees plus the value of theta, which in this case is simply going to be 138.84 degrees. Okay, and that's how you do vectors in equilibrium and resultant vectors.